as well. So it's a great hint that I'm saying. So it's like, study and evaluate yourself immediately. Something like that is going to happen today. Okay. So a brief recap. We were here. We were in this topic of TCP congestion control, and we are almost done. We started discussing we discussed three flavors of sorry, three phases of TCP: slow start, congestion avoidance, and FRFR, which is fast retransmit and fast recovery. And then we discussed the three flavors or three versions or three different algorithms of TCP congestion control, which are actually the pioneer ones, the starting algorithms on which the modern day TCP congestion control algorithms actually build upon or work upon. So TCP, TCP Reno, and TCP New Reno. So we're having this discussion, and TCP Tahoe, um, which do not include the fast recovery phase. So it basically operates using the slow start phase, using the congestion avoidance phase, and the fast retransmit phase. So it means that whether the packet loss is detected via timeout, or whether the packet loss is detected via triple duplicate acknowledgement. The behavior of TCP Tahoe will be same in both cases. Okay, whether the loss is detected via timeout or via triple duplicate attack, the behavior is same. And the behavior will be that it will immediately set the congestion window to, and then the window will grow exponentially, which means that the algorithm will enter into a slow start phase. Okay, and obviously after hitting the slow start threshold, then go back to
Sir, you're not audible.
hello, am I back?
Yes, sir, you're back.
Yes,
Yes,
sir.
sir.
Yes, sir.
No.
Yes,
Hmm.
sir.
Really, really sorry, Ji. Really sorry. As I said, the problem, I should have shifted at the very beginning. This this was Wi-Fi. So yes, okay, okay. Sorry, Ji. Sorry. Okay. So back to our discussion. I believe we were here. Okay, so Tahoe's behavior on timeout and on triple duplicate attack. So loss is detected whether timeout, whether triple duplicate attack, behavior is the same. Okay, so down to 1 MSS and up to so on. This is the FSM of TCP Tahoe. There are only two states: slow start and congestion avoidance. And if we are in the slow start phase and we are receiving acknowledgement, for each acknowledgement we are increasing the window size by 1, which means that after every round trip time we will be doubling our window size. And if we are in the congestion avoidance phase, for each acknowledgement we are increasing the window size by 1 over C wind, which means that after every RTT we will be increasing the window size by 1. So this is exactly the formula which was being shown on the animation of AIMD as well. So C wind is equal to C wind plus 1 over C wind. And we will leave the slow start state when we hit the threshold, and we will leave the congestion avoidance state when we detect a loss, whether by timeout or by triple duplicate acknowledgement. And when we leave the CA phase, we will, after detecting the loss, we will do these things. Okay, we will start from the beginning by setting the congestion window at as 1, and we will set the threshold value at the value of C wind, which was which at which we incur at which we detected this loss, divide by 2. Okay, In Reno, what was the improvement in Reno was actually that Reno use all the all the three phases. So slow start, congestion avoidance, and FR. So it does fast recovery, and I explained you guys that fast recovery is nothing but but saying something that if the loss is indicated by triple duplicate acknowledgement, then we will not be behaving exactly the same as Tahoe, because Tahoe was the first congestion control algorithm, and it was since it was the first one, it uses a very conserve approach, a very careful approach in dealing with the detection of loss. Okay, but Reno is a slight improvement on Tahoe, and Reno says that no, these two states are totally different. Okay, loss detected by timeout and loss detected by triple duplicate acknowledgement is a very, these two states cannot be classified as same states of the network. Loss indicated by timeout means I sent some packets and I received nothing in the response. This is a very worst state of the network. I will do exactly as Tahoe does. I will, so basically we can write same as Tahoe. Okay, same as Tahoe. I will do exactly as Tahoe does, but if loss is indicated by triple duplicate acknowledgement, then I will not be so careful or so conserved, because duplicate acknowledgements indicate that network is capable of delivering some segments. Okay, so when I receive a duplicate acknowledgement, it means that another new segment is received by the receiver. That's why I am receiving these duplicate acknowledgement. Okay, so this is a different state of the network. So what I will do is that my behavior will be different than Tahoe, and I will cut the window size into half instead of going back to 1. And then since I am cutting the window size in half, so obviously I do not have the luxury of going into the exponential increase phase, but I will go directly into the congestion avoidance phase, and I will grow linearly. Okay, and I ask you guys, I did not cover the new Reno. I asked you guys that you should have a look at this difference in the two algorithms, and try to fill up this table. So has anyone come up with some numbers? So I mean, in this figure, in this diagram and this table, what is shown over here is that how much this optimization bring in, how much improvement this optimization bring in. So I mean, if you see, black one is TCP Reno, and the blue one is TCP Tahoe. Obviously here the black one is not clear, because the blue one is superimposed on the black curve, because the behavior of TCP Tahoe and Reno both are exactly the same at the beginning. They both will start at C wind is equal to 1, then they will enter the slow start phase, exponentially increasing their window 1 to 2, 2 to 4, 4 to 8, and then let us assume that at the beginning we have set the slow start threshold at 8. So both of them will, after hitting the slow start threshold, because this is a random threshold at the beginning. Okay, so after hitting the threshold, both of them will convert into the linear increase. So after 8, then 9, 10, 11, and 12, and let's assume that at the 8th round trip time, when the congestion window value was 12, we detected a segment loss. Both of the TCP hosts, one running TCP Tahoe and one running TCP Reno, both hosts detected a segment loss, and this loss is indicated by triple duplicate acknowledgement. Now here is the difference between the behavior of two algorithms. The Tahoe will does what? It will go down to C wind is equal to 1, and then goes into exponential increase. And obviously C wind, the value of C wind is 12, so the threshold value will be C wind by 2. So the next time when Tahoe hit this threshold, which is 1, 2, 4, and 6, 12 by 2 is 6. After hitting 6, it will move from exponential to linear increase. Okay, so in the next RTT, one segment really sorry ji, in the next RTT onwards, one segment will be added. So 6, and then 7, and then 8, and then 9. On the other hand, triple duplicate ACK, the behavior of Reno will be different. Reno will say no. Duplicate acknowledgement means network is capable of delivering some segments. I will not go down that much. I will cut my window size into half. This is exactly like the animation. Okay, so the MD part, this MD part is different than this MD part. So the multiplicative decrease of TCP Tahoe is not actually a multiplicative decrease. It's going down to 1. But on the other hand, TCP Reno will divide will cut the window size in half, which means 12 by 6, and then obviously then it will directly go into the linear increase, okay, instead of exponential. So onward, an increment of 1. So 6 and then 7, 8, 9, 10, 11, and then 12 up to so on. Okay. So what is the what will be the difference in the number of segments? Anyone? Has anyone calculated?
Yes, sir.
Yes,
Yes,
please.
sir.
Please, anyone? बताइए ये values बताइए so that I can write it over here and share with everyone else.
सर के लिए window will be 9 and segment will be 94th. And for Reno, it will congestion window will be 12th and segment will be 120.
Segments, number of segments दोबारा बताइए kindly. ताहो के लिए
94 in Tahoe
90.
and 120th in
120.
120 and yes.
There is a breakage in voice. Someone else who has calculated 120.
सर ये बिल्कुल ठीक बताया, यही है जो आंसर मैंने बताया.
190. Okay, 94 and 120. So that's good. More than one students have calculated and they reached to the same conclusion. I mean, it's good that you guys took my words for this homework and you did it. But the point is that although exact calculation of these numbers is important in the sense of having the right answer, but the message, the takeaway message is the difference. So you can see that with this very little optimization, there's a very little difference between Tahoe and Reno. But at 15th round, because of this very little difference, Reno has already sent 26 more segments as compared to Tahoe. ठीक है जी? And which basically means in terms of percentage, it will bring about approximately 15 to 20% improvement. So and all of you guys are students, research students of MS. So that much improvement is enough to publish a new paper. That is why these three algorithms are three different research papers. Okay, and of I think Wen Jacobson himself, but they are three different research papers. Okay, so now the only algorithm remaining is TCP New Reno. It uses
Excuse me, sir.
just yes, please.
सर प्लीज ये पीछे जो सेगमेंट था इसकी कैलकुलेशन से थोड़ा सा आप बता सकते हैं?
इसकी कैलकुलेशन तो माजरत के साथ करनी थी आप लोगों ने। ये
सर थोड़ा सा
ये
एक
मेरी
आइडिया
मुझे
सर कि
बताने
सेगमेंट
ही नहीं चाहिए। अच्छा जी, चलें।
सर
Okay, so it's the calculation is very simple. We are just counting the number of segments sent in each round, and we are just adding them up. So for instance, in the first round over here, we both have sent one segment, and then in the second round, both have sent two new segments. So 2 plus 1 is 3. Okay, so two new segments and 2 plus 1 is 3 over here, okay. And then in the next round, 4 new segments, so 4 plus 3. So it will remain the same until round 8. Until round 8, it will remain the same. Obviously, it's not shown here on the table, but after round 8, in the next round, in the round 9, TCP Tahoe will be sending only one segment, while TCP Reno will be sending 6 segment. Okay, and if you add these things up, just like your class fellows have done as a homework, you will come up with these numbers after 15 segments. So after 15 segments, 15 RTTs, sorry, after 15 RTTs, the total number of segments sent by TCP Tahoe is 94, and its congestion window is 9. Well, congestion window is very easy. It is already shown over here. It's 9. You can see congestion window is 9 right here, and its congestion window is 12. So it's very easy. Its congestion window is 12, its congestion window is 9. But the total number of segments sent is, you are just adding up segments being sent in each and every RTT. Okay, Vikas? You are adding up segments sent in each and every RTT. So it's just like, until 15th RTT. Until here, TCP Reno has sent a total of 120 segments, and until this 15th RTT, until here, TCP Tahoe has sent a total of 94 segments. So that is the difference, and that is the improvement that that the trip the the Reno algorithm, which is reacting differently on triple duplicate ACK rule, brings on top of Tahoe. Okay.
Sir,
As a
thank you.
repetition, you're welcome. You're most welcome.
सर
Okay, जी. So, जी, please.
ये 94 की जो वैल्यू कैलकुलेट की है इसमें
Mhm.
हमने जो सेगमेंट्स हमने रीट्रांसमिट किए हैं उनको दोबारा काउंट किया है.
Okay. The value calculated in 94 and 120, I believe that there is only one segment retransmitted, which was retransmitted right here, and it was the fast retransmit. Both TCP Reno, very good question. I think that one is not calculated twice. These are all the new segments because that one retransmitted fast retransmitted segment was part of the 8 segments being transmitted in the 8th RTT by both the algorithm. And the students who have added up and came up with these values can confirm if they have added this one retransmitted segment or not, fast retransmitted. I believe it's not added, and the number 94 and the number 120 are the number of segments which are only new transmissions. So the retransmission, first of all, there is only one segment retransmitted, which was one of the lost segment in this 8th RTT. Out of the 12 segments transmitted in this 8th RTT, one of them was lost. Okay, and that's why we detected that loss via triple duplicate acknowledgement. Now both Tahoe and Reno both does the fast retransmit, but after doing the fast retransmit, their behavior is different like this. Okay, but that fast retransmit is not included, okay, in this number. Fahad, is it clear?
Okay, so once the MD occurs in both Tahoe and Reno, that is when the lost segment is retransmitted, or that happens before the MD?
No, that happens before, immediately after detection. First the first FR is being invoked, the fast retransmit, and after doing the fast retransmit, then the MD part will take place. Okay, so at this very point, you can, I mean, if you really want to meticalize and go into the detail of at which point in the RTT, then it may become a bit complicated. But you can say that at the start of the 9th round trip time, when the triple duplicate acknowledgements were detected, loss was detected via triple dup ACK, then immediately fast retransmit will occur. Okay, and after that, the window size will be adjusted according to their own MD part, and then the algorithm will move forward. Okay.
Okay, और सर just one thing, जब वो retransmit हो जाएगा segment जो loss हो गया था, तो acknowledgement number जो हमें मिलेगा receiver की तरफ से, वो फिर उसी segment का होगा या फिर वो cumulative ACK होगा फिर?
No, that will be a cumulative ACK. Very good question. Again,
ठीक है, thank you, sir.
this will be cleared in New Reno as well. Okay, but good question. That will be a cumulative ACK. Okay, so everyone got the question from Fahad. After the fast retransmit, the acknowledgement number that the receiver will send after receiving the fast retransmit segment will be a cumulative acknowledgement. Okay, of not only the packet which was received as a result of fast retransmit, but also all the other packets which are received out of order. Okay, and up until the last one. So it will be a cumulative acknowledgement. Good questions. Okay, so the difference between Reno and New Reno. So let's, I mean, we are going incrementally. First algorithm Tahoe, then Reno, slight improvement, then New Reno, another slight improvement. So New Reno is a bit more greedy. New Reno says what? Again, loss indicated by timeout, same as Reno. Now, same as Reno means what? If the loss is indicated by timeout, the behavior is same as Reno, which means
Got
One
one
divided by
MS.
two.
Congestion window will be go to 1.
Same
which
as
means
Tahoe.
same as Tahoe. Yes. Okay. Loss is indicated by timeout. New Reno also agrees that, okay, if this is a timeout, this is the worst state of the network. I will do exactly as Reno is doing, which is exactly as Tahoe is doing, which means, as all of you have said, cut the congestion window to 1, okay, not half. just go down to 1, okay, and start from exponential increase once again, okay, because when you bring your congestion window to 1, it is, basically you are giving a margin of a complete round trip time to the routers in the middle to empty out all of their buffers, okay, because timeout indicate a very worst case. But on the other hand, loss indicated by triple duplicate act. Now, as I said, New Reno is a bit more greedy as compared to Reno algorithm. Okay, so Reno does what? Reno says, okay, if loss is indicated by triple duplicate ACK, I will not do as Tahoe is doing. Okay, Tahoe is just reacting the same way like timeout. It is going to 1 and then exponential increase and up to so on. I will do what? I will do cut congestion window into half and then linear increase. TCP New Reno says that during that RTT, when I will cut congestion window into half, obviously plus 3 is for the 3 duplicate acts that I received before the fast retransmit, and also apart from that, all the other duplicate acts that I keep receiving, I will also send one new segment for those acts. Okay, uh, so basically this concept is called congestion window inflation. Okay, and New Reno uses this concept. So
Sir,
the point is that
repeat kar, please?
I will repeat this both in English and Urdu. I am not done in English either. So the point is that New Reno is doing. So for instance, if we have I need some white space to give an example. Okay, right here is fine. So if we have an example, a situation in which let's say we transmitted packet 1 and then packet 2 is lost immediately after packet 1 packet 2 is lost, and then the rest are being received correctly, but we know that after P3, after P3, I mean you're following, it's not a clean drawing but you're following. After P3 up to, let's say, window size is 16, n is equal to 16. After P3 up to P16, we will be receiving a whole lot of duplicate acknowledgements, many duplicate acknowledgements, and this example is more or less similar to the animation example, in which if the window size was 16 or 17, let's say, and we after the empty part we cut it into half, but then there were many duplicate acknowledgements that we wasted, and we did not. If you recall the animation, okay, running it again will take some time, so just recall it. uh, and obviously you can see it right here in this time sequence diagram as well, that if we just right here when we detect the segment loss, because we will receive an acknowledgement, okay, which is over here, which is ACK of 2, and then we will receive uh, after receiving packet 3 another ACK of 2, and then packet 4 another ACK of 2. So one original and 1 2 3 third duplicate acknowledgement after receiving packet 5. Okay, over. uh, no, it's not that clean. Should be something like that. Okay, so packet 3 4 and 5, after packet 5 we will be receiving the third duplicate acknowledgement, and we will fast retransmit. But the thing is that after that there will be many other I mean, because these segments were transmitted in the previous RTT. Okay, these segments were transmitted in the previous RTT. So after packet 5, packet 6 up to 16, there are further many duplicate acknowledgements which we will keep wasting. Okay, so New Reno just say something like that. And now if you read the sentence, you will understand. Duplicate acts, again same sentence, indicate network capable of delivering some segments. We will do what? We will cut the window size in half plus 3. Okay, just like Reno. This is more or less like Reno. Reno does that, but be, between the time when the fast retransmit occur and the time when the new acknowledgement, just like Fahad asked the question, the new cumulative acknowledgement is received, until that time we will keep growing the windows linearly. Okay, which means that for every duplicate acknowledgement, so New Reno is doing something like that. I mean, okay, that I'm being greedy in the sense that I do not want to wait any duplicate acknowledgement. I believe that one of the packet was lost just because of an instantaneous congestion state of the network, or maybe due to corruption or something else. Because I mean, even if the packet is received in the corrupt form, even in that situation, I will be receiving duplicate acknowledgement. So I will, because the receiver is actually trying to ask me for the retransmission. Okay, so it is receiving the new packets. So the new Reno is only thinking, or you can say that the behavior of new Reno is only like this, because for each duplicate acknowledgement, it is believing that the network is capable of delivering one more new segment. So I am going to transmit one new segment. Okay. So if an acknowledgement is received, whether it is duplicate or not, I will still keep my behavior of the linear increase, which I was doing in the case of congestion avoidance. Okay. So C wind plus equal to 1 over C wind. Okay. This is exactly the formula of CA, right? So I mean, in this example, for instance, when it receives another duplicate, so P6 is received, P6, fast retransmit occur over here. Okay, fast retransmit occur over here. Now, when P6 is received, before this fast retransmitted segment reaches the other end and the new cumulative acknowledgement is received. Ali, please mute your mic. Okay. Before this fast retransmit, this is a time of half RTT. Okay. When this fast retransmitted segment will reach to the receiver. Okay. You are getting my point. In between this time, we will be receiving further more duplicate acknowledgement depending upon the size of our window. And especially if our window size is high and error occurred at the beginning of the window. Okay. Just like this, just like the example I have portrayed over here. In that case, for further duplicate acknowledgements, I will keep transmitting new segments. So fourth duplicate acknowledgement received, packet 17 is transmitted. Fifth duplicate acknowledgement received, packet 18 is transmitted, and up to so on until I receive a new cumulative acknowledgement, and then I will leave the fast recovery phase. Okay, it is shown. It is much clear when it is shown over here in the FSM. So if we just look at the FSM, I will let me repeat all these things. This is the last slide of the chapter, of the lecture, of the topic, and of the transport layer, and it's an all important slide. This is the FSM of TCP New Reno, by the way. Okay, not Reno, not Tahoe. This is the FSM of New Reno. So if I just repeat all these things and over here in the FSM, and then let's see if there is any confusion or question that persists. Okay, the these states are quite clear, but let me just repeat. These states are exactly the same as the behavior of Reno. So we are in the slow start phase. This is the starting state. You can see this arrow is showing that this is the starting state, and we do nothing. At the very beginning, we set our congestion window as 1 MSS. Our slow start threshold is 64 kb. This is the by default threshold as per my knowledge in internet. Maybe it's changed for in the modern internet, but some years ago it was this threshold. It's a safe value after 64 kb at the very beginning, because you don't know the state of the network, and duplicate ACK count is 0. Okay, you start in the slow start phase. Now there are 3 events possible. Okay, one event is that which is the correct working. You keep receiving new acknowledgement. What you are doing is that you are increasing your window size by 1 MSS. Okay, this is an exponential increase. Okay, you receive a new acknowledgement, you increase your window size by 1 MSS, and you keep your duplicate ACK count as 0. I mean, if there was some duplicate ACKs being counted before, you will immediately convert it into 0 because a new acknowledgement is received. Okay, a new acknowledgement is received. So at the receipt of new acknowledgement, obviously your duplicate ACK count must be reset to 0 if there were any before. And as it's written here, transmit new segments as allowed. Now we have already seen in the time sequence diagram, that in the slow start phase, we are allowed to transmit 2 new segments. We have already seen over here. Okay, so when we receive an acknowledgement, we transmit 2 new segments, and the reason is one is transmitted for the for the received segment, and more is transmitted because the window size keep increasing by 1 on each acknowledgement. On each acknowledgement, we are running the formula C wind is equal to C wind plus 1, which is exactly like this. C wind is equal to C wind plus 1 MSS. To transmit new segments as allow means that you are going to on each acknowledgement 2 segments, one to cater for that acknowledgement and one new which you are allowed because of the increase in window size. Okay. Second event can be timeout. Whenever timeout occur, whether timeout occur over here, whether timeout occur over here, or whether timeout occur over where is the third one? Where is the third one? Over here. Okay. Where
सर आपकी आवाज चली गई है.
who muted me? अच्छा जी. Who muted me जी? Who is right? Okay. Challenge. Let's not linger on. Whoever it was, kindly don't do this. I hope it was a mistake. I was saying whenever timeout occurs, the behavior is exactly the same. Whether you are in the slow start phase, whether you are in the congestion avoidance phase, or you are in the fast recovery phase. We already have learned that at timeout, Tahoe, Reno, New Reno, although this is the FSM of New Reno, we have learned that Tahoe, Reno, New Reno, all of these three algorithms does the same thing. They set their threshold as C-wind by 2. They take their C-wind to 1 MSS and they move to slow start phase. So if they are already in the slow start phase and timeout occur, it's a self loop. If they are in the congestion avoidance state and timeout occur, they will do all these things and move to the slow start phase. And if they are in the fast recovery and timeout occur, Saad, please mute yourself. Saad, please, you have a question, Saad? Or we are in the fast recovery phase. In the case of timeout, these things will happen. These actions will be performed, and you move into the slow start phase. Okay. Right, and the third event is the duplicate acknowledgement. If duplicate acknowledgement is received, you will just increase the duplicate count, increment the duplicate count by 1. Okay. Right.
Sir, एक क्वेश्चन था इसी से.
Yes, I've not completed anyway the FSM. Anyway, keep going. Please ask.
सर जो आपने ऊपर डायग्राम बनाई थी जिसके अंदर आप कहते थे रिपीटेड एक्स आएंगी जो कि
डुप्लीकेट
नहीं हमारे डुप्लीकेट एक्स आएंगी.
Yes.
तो उसमें तो वो डुप्लीकेट एक्स नहीं आएंगी जब वो पैकेट नंबर 3 जो मिस हुआ था हमसे वो जब दोबारा रिट्रांसमिट होगा तो नेक्स्ट एक्सपेक्टेड पैकेट तो पैकेट नंबर 16 है तो हमारे पास डायरेक्ट एक्स 16 की क्यूमुलेटिव नहीं जाएगी.
16 की एक आने से के दरमियान में there is a lot of time. There are 16 segments being transmitted, and these segments are transmitted one after another, just like the concept of sliding window, just like we have been studying for past many lectures. So if packet 2 is being lost, packet 3, 4 and 5, after the receipt of 3, 4 and 5, 3 duplicate acknowledgements will be sent. Okay, but the duplicate acknowledgement will not stop just after sending. So the behavior is the same. The algorithm says if you receive a segment out of order, just transmit the oldest acknowledgement of the last in order received segment. So after receiving 6, 7, 8, 9, 10 up to 16, the receiver will keep transmitting duplicate acknowledgement of packet 3. So ACK 3, ACK 3, ACK 3. Although fast transmit has already happened, but it will take another half RTT for the retransmitted segment to reach. Okay. Yes. Between this, yes. Okay. Thank you for your question. Okay. Uh, I think that it took more time. Anyway, let's just conclude. We'll see what we'll do about the quiz. Um, Obviously, we may have to take it tomorrow, uh, because you guys need at least 15 to 20 minutes to download and then do it, solve it, and then upload it over LMS. So we may take the quiz tomorrow. Right. So we are here, but this discussion is important. So uh, keep listening. Okay. What else is remaining? So when we are in the slow start, we have already discussed all the three events in action. Let's move to the congestion avoidance. We know in the case of the new acknowledgement, although it's a very fancy formula is written over here, but trust me, it is exactly the same as C wind is equal to C wind plus 1 over C wind. Okay. What we are doing is that 1 over C wind, we are trying to find the proportion of that 1 over C wind part in terms of MSS. That is why we are writing it like this. Okay, the formula is exactly the same, and as it's written here, that transmit new segment slash or segments as allowed. Now we know that we will transmit one new segment, but if the C wind is increased, just like the animation, and we have accumulated enough ACK that after RTT C wind is increased by one segment, then we will transmit a small burst of two segment. Just try to recall the animation. So it's exactly the same. And in the case of duplicate ACK, we will just increment the counter of duplicate ACK, and we will keep a track of this counter. And if we detect that the duplicate ACK count has reached to 3, then this is the point when we leave the slow congestion avoidance phase and we will go to the fast recovery. Obviously, we will fast retransmit the missing segment immediately. But within the fast recovery phase, what we will be doing is that for each new duplicate acknowledgement, we will be transmitting one new segment, okay, to counter for the duplicate acknowledgement. And we will stay in this phase until we receive what? We receive a new acknowledgement, okay, not a duplicate. If we keep receiving duplicate acknowledgement, we will keep transmitting the new segment and we will remain in the fast recovery phase. But when we receive the new acknowledgement, then we will do something like that. We will set the C wind value as SS thresh, and remember the SS thresh contains a value of C wind by 2. Okay, C wind by 2. We store this value in SS thresh before when we were leaving the congestion avoidance state and moving towards the fast recovery state. So if we are setting this congestion window value to SS thresh, it basically means we are setting it to a value of C wind by 2, and this C wind by 2 is the value that was that was there when we actually detected the triple duplicate acknowledgement. Okay. This is exactly the same if we move from slow start to fast recovery. So this over here and this over here, they are both exactly the same. And whenever we move towards slow start, this and these three are exactly the same. We are moving towards slow start, whether from slow start to slow start, or from fast recovery to slow start, or from congestion avoidance to slow start and up to so on. Okay, so the FSM, it seems difficult, but it's not that much because many of the events in action are actually repeated, right? Okay, so this is the concept of New Reno and uh, congestion control, TCP congestion control. Obviously, in these last 2-3 slides, it's just TCP versus UDP revisited.
सर
We
ये
already know.
रेनो और न्यू रेनो के कंपैरिजन का कोई ग्राफ है?
Yes, you can find it over internet maybe, but unfortunately I don't have it in slides, and it is also not present in the um, in the books, in both the books, in the book of Berose Frozen and in the book of Kuros and Ross. Okay, um, uh, this sort of comparison would be very interesting because we would like to see that this how much improvement this optimization is bringing on top of Reno. Okay, you can refer to the original paper of Van Jacobson. Okay, which was back in 1990 or 1991. If you just Google Van Jacobson New Reno, TCP New Reno, you will find that original paper. I believe in this inside that paper, because even Van Jacobson was giving New Reno as an improvement on Reno. So he was comparing the performance of algorithm with the previous version. So I think inside that paper you may be able to find some empirical analysis, some statistical detail, but unfortunately it's not part of books or slides. Okay, but definitely the improvement is there. Okay, I don't know in terms of percentage or like the way we calculated over here, I don't know like that, but it is there is a slight improvement, obviously, because of the number of segments that are being transmitted against the duplicate acknowledgements, which in case of Reno are being wasted, okay, after fast retransmit. All right, so the final words are here. We already know difference between TCP and UDP, so there is no need to, we know that UDP has datagrams, TCP has connection, and all those things, and these are the advantages of UDP, but obviously at the cost of doing very little on top of IP, while TCP does quite a lot of things on top of IP. Okay. They are talking about fairness and parallel TCP connections and things like that. So what will happen? But I mean, these are fairly straightforward discussions. We have already done that, and this is the ground that we have covered in the past 4 or 5 weeks, maybe, or even more. And now we can leave the network edge, and we can move towards the core of the network, which is the network layer and the data link layer. Okay. So here I stop recording and of this